Dear ladies and gentlemen, I'm gonna introduce you to my doctoral thesis, which applies micromechanic techniques to cementitious materials. The aim of computational micromechanics is to establish links between the microstructural properties and the macroscopic behavior. Cementitious materials are particularly challenging to be used in multiscale mechanics because they present evolving microstructure at early ages and the solid constituents and the porosity ranges over several orders of magnitude, from gel pores of a few nanometers until aggregates in concrete of few centimeters. The first of my contributions to computational micromechanics was the derivation of the strain and stress average rules from the principle of virtual power. This provides a solid framework to micromechanics modeling. Next, a homogenization scheme was developed to study complex materials. By complex materials, I mean those whose microstructure is not adequately described by homogeneous phases. For instance, in cement paste, the solid CSH does not have the same density everywhere, and therefore, the mechanical properties may differ from one point to another. Using these functions, we were able to solve an implicit integral equation to calculate the effective properties of these materials and the microscopic strain and stress fields. Regarding anisotropic matrix inclusion composites, a homogenization scheme was developed to study the average strain and stress fields in the matrix and inclusion phases. This is particularly relevant for modeling extruded materials, like, for example, 3D printed concrete and other cementitious materials. For micromechanics modeling, it is also very important the volume fraction of the material. Therefore, we develop a hydration model based on protonuclear magnetic resonance. One test of NMR provides 4 quantities, which relate to the hydrogen present in the capillary pores, in the gel pores, in the solid CSH, and in the calcium hydroxide. This gives the motivation for an innovative conceptual approach, and is to focus only on the subsystem of cement paste which contains hydrogen. This led to the introduction of the precipitation degree, which is quantified as the amount of hydrogen in the reaction products divided by the total amount of hydrogen in cement paste. 3 samples, cured under sealed conditions with different water to cement mass ratio, were used to calculate the 3 parameters which define the evolution of these populations as a function of the hydration of the precipitation degree. And these parameters were validated using samples cured in different conditions, this time underwater, with different temperatures. And as we can see, the evolution of these quantities as a function of the precipitation degree is independent of the initial composition, temperature, and the storage condition. This allows to calculate the volume fractions not only of the phases containing hydrogen, but also of the clinker and the airfield voids. These volume fractions were used to study the swelling of mature cement paste during the isothermal absorption. This test measured both the water content and the macroscopic strain at different internal relative humidities. Our aim is to develop a multi-scale poroelastic model which takes the evolution of the water content as an input in order to predict the macroscopic volume changes. This is done representing mature cement paste as a 4-step matrix inclusion homogenization scheme. We have pores which, under partial saturation, may be either filled by air or by water, and the pressure in these pores will depend on the relative humidity. The average effective pore pressure in each pore family will be obtained integrating over the pore size distribution, and the nanoscopic deformation in solid CSH will be identified in one of the samples and used together with the pore size distribution obtained from absorption porosimetry to predict the macroscopic strain of the sample with satisfactory results, as we can see. Thank you for your attention.